This is an innocent-looking integral that lead many to mathematical sins. Let me show you why. First, here's the common mistake. In order to use the power rule of integration, we write this as the integral from -2 to +1 of x raised to -2 dx. Then, applying now the power rule, this becomes x raised to -2 plus 1 over the same numerator, -2 plus 1, from x equals -2 up to +1, which is simplified as x raised to -1 over -1 from -2 up to +1, or finally, we have -1 over x from -2 to +1. Solving now for the value of this integral, we have the value of the integral equals -1 over this upper limit of integration, which is 1, minus -1 over the value now of x is -2, and this simplifies to -1 minus +1/2, or -3/2. Now, this answer is wrong. Why? The reason is we go back to the given 1 over x squared. Now here, x squared cannot be equal to 0, and therefore x is not equal to 0. But our limit of integration, remember, is from -2 to +1, which contains x equals 0. And if you are going to graph 1 over x squared, its graph would look like this. There is a vertical asymptote at x equals 0, vertical asymptote at x equals 0, and the graph of 1 over x squared looks like this. And we would like to find the definite integral from x equals -2 up to x equals +1. So we would like to find this area, but x cannot be equal to 0 because that is our vertical asymptote. And therefore, we have a problem here because we have a negative area. Remember, the result of definite integration is the area under the curve. But our area here is we have a positive area at the left side of 0, and we have a positive area at the right side of 0. Therefore, we do not expect a negative definite integral value here. So definitely, this has a problem. So how do we correct this problem? To correct this, we are going to find the area from -2 up to 0 approaching from the left, or 0 minus. We are getting closer and closer to 0, but not touching 0. And the other part is find the definite integral from 0 coming from the right up to +1. And so we can break this down into two definite integrals. And since we are only approaching 0, but not actually 0, we are also going to use the concept of limit. So we now say the integral from -2 to +1 of 1 over x squared dx is equal to the limit of the definite integral from -2 up to certain constant, and let's call it as a, of the function 1 over x squared dx as a approaches 0 from the left, plus the limit of the integral from, let's use another variable here, from b to +1 of 1 over x squared dx, where b is approaching 0 from the right. In this way, we have taken care of the vertical asymptote, that is that x cannot be equal to 0. It comes closer to 0 from the left and from the right, but not equal to 0. So, simplifying this, we now have the limit as a approaches 0 from the left. Then let's evaluate this definite integral. We know is -1 over x, so this is equal to -1 over x. X is from -2 to a, plus the limit as b approaches 0 from the right of the same function, -1 over x. X is from b up to +1. Then evaluating, this is equal to the limit as a approaches 0 from the left of -1 over a minus -1 over -2, plus the limit as b approaches 0 from the right of -1 over x equals 1 minus -1 over x equals b, where b is approaching 0 from the right. And so we now have two limits here, this one and this one. If we can show that at least one of these two limits diverges, meaning to say the value goes to infinity, then we say that this definite integral diverges. In some books, it says that the value of the definite integral goes to positive infinity. Now, let's evaluate this. What happens to negative 1 over a if a becomes close to 0 from the left? So we'll have here negative 1 over a very small negative number, let's say 0.000001. What can we say about this value? You have a negative number divided by a very, very, very small, extremely small negative number. We say that the value of this approaches positive infinity. Therefore, this part here is positive infinity, because even if you subtract positive 1/2 from infinity, it will not make any difference at all. So this part here is infinity minus 1/2 with still infinity. Now here, this part here is negative 1 minus, then you have negative that becomes positive 1 over b. Now you have here a positive number divided by an extremely small positive number because b approaches 0 from the right. Then this part here would also be infinity. And negative 1 plus infinity would still result to infinity. So you have here a value that approaches infinity and another value that approaches infinity. Then we now say that this integral diverges and we cannot find a definite finite solution for the area of this shaded region. And that is very intuitive because this function goes to positive infinity as it approaches 0 from the left and 0 from the right. And so there would always be an additional area to be added to the total area. And intuitively, we say that the area of this shaded region would be infinity. But in many Calculus 2 books, you'll find out there that they would just say, this definite integral diverges. And it's enough that if you can show just at least this one part to diverge, then you do not need to evaluate this part because the entire definite integral already diverges. So this was an innocent looking integral, but if we are not careful about the restriction that x cannot be equal to 0, and we are not mindful of interpreting this definite integral as the area of this shaded region that is definitely positive while our analytical result is negative, then we would assume that this is the answer. So the takeaway here is always check for the restriction whenever there is division by 0 and interpret your result by visually inspecting the graph of the function if the result really makes sense or not. And so we are done. Thank you very much. This is Land Assistant and we hope to see you again in our next video. Bye for now.